And so our next speaker is also remote. John Weaver from the Cosmic Dawn Center. And he's going to talk about a method to distinguish quiescent and dusty star-forming galaxies with t-SNE.
All right, great. Can you hear me?
Yes.
Fantastic. All right. Hi, everyone. My name is John Weaver. I'm a PhD student at the Cosmic Dawn Center here in Copenhagen. I wish I was there with you today, but okay. I want to thank the organizers for giving me the opportunity to talk about this work. This was done in collaboration with some of my fellow colleagues here at Dawn and also some students and other folks at Caltech over the past 3 or 4 years or so. So I'm going to take a few moments of your time to talk about In Search of Fossils, a method to distinguish quiescent and dusty star-forming galaxies with t-SNE. So this is I'm an observer. I love these kind of images. This is a wonderful picture of the Hickson Compact Group 87, and it shows all of our main players in this story today. We have our star-forming galaxies, we have our quiescent galaxies, and we have our dust lanes and our dust obscuration. These are what we're going to be talking about today. So the current paradigm, just to remind everyone, is that, of course, galaxies grow by forming stars. They might form also by mergers. But we know that at some point, at least a fraction of them seem to have stopped forming stars. These are our quiescent galaxies. And so I would call these quiescent galaxies fossils, right? They're the fossil record. They contain the record of everything that's happened to them. And that's where it's really interesting and where we can go dig and find out the story of galaxy evolution. And so now the question is, what do we want to learn? What do we want to learn about these quiescent galaxies and their story? So the physics question, right? What mechanisms drive galaxies to cease star formation, to turn into these quiescent galaxies? And I think more interestingly, perhaps, is the statistics question. What fraction of galaxies have stopped forming stars? And at what epochs is this happening? And so I'm going to focus on the second question here today. And so this is one of probably the most interesting figures in galaxy evolution studies, certainly one of the most pivotal. This is looking at the cosmic star formation rate as a function of time. And as you can see in the very distant universe, we're bringing up the cosmic star formation rate. And then at redshift 2, we hit the peak, the so-called cosmic noon. And then we in the local universe, have a dearth of star formation. And so the nearby galaxies, of course, are beautiful and resolved, and we can learn all sorts of things about them. And that's been an enormous field of study that has taught us so much. But of course, if we want to learn about the evolution, then we have to deal with distant galaxies that are, of course, much less resolved. We have a lot less information. And of course, these distant galaxies are much more difficult to measure. The measurements are less accurate. The samples are typically incomplete, whether that's flux incompleteness or mass incompleteness. They're vulnerable to selection biases, especially if we don't understand necessarily the astrophysics that we're looking at. And they're subject to dubious low-Z priors in terms of what is the expectation of the high redshift universe. And of course, if we take what we expect to see and we apply that, we might get all sorts of crazy stuff out. And so now, how can we begin to learn about these high redshift galaxies? Now, this has been something that's been mentioned plenty of times here. I just want to remind folks, these are our photometric redshifts, right? So we take our photometry, we assume some basis of template spectra or some spectral library, and out comes redshift and physical properties, or an estimate thereof. And so what I mean by that is we have our star-forming galaxy here. Let's say its distant cousin. We see in 3 bands. Those bands trace out a star-forming spectrum like this, and we can get some idea of its rest frame properties. Now, on the other hand, as I mentioned, we have our quiescent galaxies. These are much redder, and we can see again that these same 3 bands would look something like this. We see a red spectrum, it traces out a quiescent galaxy, and we can distinguish the two. We can distinguish the two even at very high redshift, and that's absolutely wonderful. However, star-forming galaxies don't all look like this. They don't all look like blue spirals, right? We know that a fraction of them, and this is a part of ongoing research, I'm not going to say exactly what that fraction is, we don't know, are dusty star-forming galaxies. And in fact, when you add dust on top of a star-forming galaxy, we get a degeneracy where we cannot tell apart dusty star-forming galaxies from quiescent galaxies when we have these very distant sources where we don't have all this resolved information. But again, if we want to understand the evolution, we want to understand the fraction of quiescent star-forming galaxies over time, we have to contend with this degeneracy. And so given the photometric similarity of quiescent and dusty star-forming galaxies, how can we hope to tell them apart? So the traditional approaches, on the left-hand side, I show UVJ selection. This is basically taking two rest frame colors and being able to separate out star-forming galaxies here in the bottom from dusty star-forming galaxies in the top right from the quiescent galaxies in this box, where you can see we're making a very strict selection. There's been a number of papers who have tried to break this down into looking at probability of ending up in the UVJ box. But this is certainly one way to do it. But the UVJ selection is somewhat of a remnant back where we didn't have a ton of photometric bands, right? We only had 3 or 4, and so we had to come up with ways to do that. And so now that we have many more bands, especially say in Cosmos, where we have more than 30 bands over 2 square degrees, we can begin to look at things like fitting with SED templates and running photometric redshifts and getting estimates of, say, star formation rate and selecting quiescent galaxies based on that. So that's what I'm showing kind of here on the right-hand side, this template fitting approach, and then measuring quiescence based on star formation rate. However, we want to see what happens with t-SNE. How can we improve on these methodologies? How can we break away from assumptions of templates and bases? In other words, how can we let data speak for itself? And so here we take rest frame magnitudes. So we're taking the redshift out of it. We're taking the rest frame magnitudes basing on the nearest observed frame magnitudes. And we're throwing a bunch of redshift 1, more or less redshift 1 galaxies from the Cosmos 2015 catalog at a t-SNE map. And so as you can see here, we get this clustering of SEDs. So here, for example, in red are 2 SEDs or 2 galaxies that end up very close nearby in this t-SNE map, and they have very similar SEDs. Same thing with these 2 in green. So in principle, t-SNE is able to cluster galaxies with similar SEDs, so one would expect then that we can then use it to go and look at quiescent galaxies. And so we're going to define quiescence as a UVJ selected galaxy, but with no 24 micron MIPS detection, where MIPS is an excellent way of trying to figure out if the galaxy has dust or not. And so this is going to be our quiescent label for a training, for not a training, but a scoring population, a scoring sample. And so here are 2 maps taken with the same sample, roughly at redshift 1. These are from photometric redshifts in Cosmos 2015. And we're taking 50% of the population and we're labeling them as either quiescent based on UVJ plus no MIPS or star forming. And then the other 50% we're going to call tests. Now we're going to allow the test galaxies to be scored based on their neighbors. So if you sit in a region of high quiescence, you would expect that the test galaxies would also return a score of quiescence. And oppositely, if you sit in a region of high density of star-forming galaxies, you'd expect that the voting system would reflect on that for the test sample. And so the result at redshift 1, compared to a specific star formation cut, where we're asking based on the SED fitting what would be a quiescent galaxy, and we're comparing that to our labels that we came up with. So we're pitting the template fitting approach to the t-SNE fitting approach. And so here we see an ROC curve looking at the false positive rate on the x-axis versus the true positive rate on the y-axis. And we see that the area under the curve from t-SNE roughly performs the same as the template fitting at redshift 1. Okay, so now we know at redshift 1, t-SNE and traditional methods are roughly on par with each other. If you perturb the sample, t-SNE achieves a slightly better ROC in roughly 63% of trials. So it still is significant, but maybe not the huge gain that we might have expected. But how can we maybe approach this at a higher redshift where we know that the template fitting is more subjected to our assumptions of astrophysics? In the low redshift universe, it's subjected to our template set that we've given to the template fitting code. So now we've gone and done that same test. So it's the same galaxies labeled at the redshift 1. Those are going to be our scoring set. And then our test sample is now at redshift 2. So we've mixed them together, run them with a new t-SNE map, and we've scored this new test sample at redshift 2 in the same map as our redshift 1 sample, using the redshift 1 as our labels and seeing how they can score redshift 2 in the t-SNE map. And here we see that we actually gain a significantly better area under the curve. And so t-SNE achieves a better area under the curve in 100% of trials relative to template fitting approaches. And so t-SNE enables a cleaner selection of quiescent galaxies than traditional methods. Well, we want to know why. Well, okay, t-SNE uses all the available data. We've given it all the bands that we've computed. I think it's something like 9 or 10 bands from rest frame photometry, as opposed to three bands in a UVJ selection, for example. All right, it's free of astrophysical assumptions. Of the template fitting and so on. And you can tune then for high purity or completeness depending on your science goals. However, of course, the question that we've all been asking is how can we apply these methods? So while t-SNE may be able to produce more robust distinction between quiescent and dusty star-forming galaxies, especially at high redshift where that gain is higher, it cannot readily be applied to new samples. And this is a fundamental limitation because formally t-SNE scales with the square of your data set. And it has to be tuned every time. So even if we want to take a new observation, a single new galaxy, we'd have to retrain and retune the t-SNE map. So this is clearly not going to be appropriate for the coming near future era of these large catalogs from, say, LSST, Euclid, Roman, et cetera. So we need alternatives. And I think Dan, who's speaking after me, will have something to say about that. So can t-SNE distinguish between quiescent dusty star-forming galaxies? I would say yes. But as I said, we're going to need some other solutions for the future. And just before I wrap up, I want to make a quick pitch for the Cosmos 2020 catalog. Again, I'm an observer, I'm a photometer. This is work that has been done partly at the EIP with a bunch of folks sitting in the audience. The catalog should be released later this month, hopefully be an archive in the next week or so. It's been just accepted to AppJ. And so this should be a really wonderful resource for anyone looking to benchmark codes and compare with the latest from photometric redshifts in these deep galaxy surveys. And with that, I'll say thank you.
Thank you. Thank you very much, John. Are there any questions? Well, you think about that. I have one. So we've seen already some talks before of people using sums to do a similar decomposition, and actually sums don't suffer from this caveat you showed about t-SNE. So did you compare first? And second question is, I think Yari showed that you can directly estimate the star formation rate from the sum. So without going through a classification step, you can straight go to the SFR. So why not doing that instead of classifying?
Yeah, thanks for the question. So have we tested against SOM? We haven't done that yet. This was it was a proof of concept. I think we can certainly look at other approaches exactly like a SOM. That's kind of what I was getting to by referring to Dan's talk. And I can see he's got a smile on his face. I'm sure he'll mention that in a second. So I'll defer to him for that. And in terms of what you said about Yari's work, yeah, I think the SOM is definitely a way forward, and we can do that. It's just with t-SNE, this is something we had on hand, and it was something we were wanting to prove a proof of concept at the very least. And I think this work has done this. It's brought forward this problem so that we're thinking about this more, because we certainly need to solve it, especially since we don't have MIPS anymore. We're not able to classify future samples with this. And so we'll need to find ways to do that are data driven. And I think this work has done that successfully. Thanks.
Yes. Okay. Any other question? Thank you. I think we have time for one more. I read something on Slack. There are a couple of questions which are similar, asking about other dimensionality reduction methods. So TD is asking another question about if I understood correctly, the specific star formation rate is derived by template fitting. So how is that t-SNE provides better estimate than SED fitting, especially since the input is rest frame photometry from the model?
Yes, sure. So there is some circularity here, but with the rest frame photometry, I absolutely agree. We're not trying to. This is why I said it's a proof of concept. There's improvements to be made. The rest frame photometry here is actually being derived from the observed frame, the nearest observed frame photometry.
We lost you. We lost the sound. Is your mic working? Anyway, since we need to move on to the next speaker, we cannot hear you, John, sorry, but you can answer on Slack. Thank you very much, and we will thank you. We can thank John again.